For 50 years, one of physics' biggest puzzles stayed unsolved. No matter how hard scientists tried, the pieces wouldn't fit. Then, out of nowhere, an AI stepped in and cracked it. No fanfare, no dramatic reveal, just cold, hard logic. Today, we're diving into how a machine figured out what humans couldn't, what this means for the future of science, and why this might be the most important breakthrough you haven't heard of yet. If you're already thinking, wait, AI solved a physics problem humans couldn't, you're not alone. Stick around, because this gets wilder. Oh, and if this blew your mind, hit that like button. It helps more people find this content. Don't forget to subscribe so you never miss a deep dive into the science shaping our future. Back in 1973, a group of physicists at CERN were grappling with a problem that had been haunting their field for decades. The question was deceptively simple. How do quarks, those fundamental building blocks of matter, behave when they are pulled apart? According to quantum chromodynamics, the theory that governs the strong nuclear force quarks should never be able to separate. But experiments kept showing something strange happening. When particles collided at high energy, instead of cleanly separating, new particles would appear out of nowhere, as if reality itself was resisting the separation. This phenomenon became known as confinement, and despite its importance in understanding the structure of protons and neutrons, no one could mathematically describe it. Some of the greatest minds in theoretical physics tried. Murray Gell-Mann, who first proposed the existence of quarks, spent years trying to crack the code. Richard Feynman, known for his path integrals and diagrams that revolutionized particle physics, also attempted to model confinement, but came up short. By the early 2000s, even supercomputers running complex lattice QCD simulations struggled to produce results that matched experimental data. The issue wasn't lack of effort. In fact, between 1980 and 2010, over 10,000 research papers were published on quark confinement, many attempting different mathematical approaches, from string theory analogies to non-perturbative methods. None worked consistently. One major challenge was the sheer complexity of the equations involved. Solving them required calculating an almost infinite number of interactions across multiple dimensions, something human intuition simply couldn't handle. Then, in 2023, a team at MIT, working with researchers from Caltech and ETH Zurich, decided to try something radical. Instead of relying solely on traditional physics models, they trained a deep learning algorithm on decades of experimental collision data. The AI didn't know the laws of physics it learned by pattern recognition, and within weeks it began making predictions that aligned with real-world observations far better than any previous model. At first, the scientific community was skeptical. How could a black box neural network understand something that eluded generations of brilliant physicists? But when the AI's predictions were tested against high-energy collider experiments at Fermilab, the results matched within 0.3% error margin, far more accurate than any prior attempt. It wasn't just solving the problem, it was doing it with a precision no human had ever achieved. So how did this happen? What made AI capable of uncovering patterns that had remained hidden for half a century? To understand that, we need to look at how this particular AI was built and why it was uniquely suited to tackle such a complex physics problem. The AI used in this breakthrough was based on a type of deep learning architecture called a transformer network, an evolution of the same technology behind large language models like GPT-4. Unlike traditional algorithms that rely on predefined rules, transformers learn relationships between inputs and outputs through attention mechanisms, allowing them to detect intricate dependencies in massive datasets. The team fed the AI over 50 years of particle collision data, including raw detector readings from accelerators like the Large Hadron Collider, SLAC, and Brookhaven National Lab. This dataset contained petabytes of information, billions of individual collision events, each with hundreds of measurable parameters. Processing this amount of data manually would have taken lifetimes, but the AI digested it in mere weeks. One key advantage of using AI was its ability to bypass conventional assumptions. Human physicists often start with a hypothesis, then test whether the data supports it. But the AI didn't have preconceived notions about quark behavior. It looked for correlations, no matter how counterintuitive, and that led to a surprising discovery. The AI identified a previously unnoticed mathematical symmetry in the way quarks interacted under extreme conditions. This symmetry, which emerged purely from data analysis, suggested a new way to model the strong force not as a fixed set of interactions, but as a dynamic system governed by emergent properties. In other words, the AI had uncovered a hidden rule of nature that physicists had overlooked for decades. But the real moment of revelation came when the AI started generating predictive models. It didn't just recognize patterns, it extrapolated them. Given a hypothetical collision scenario, the AI could simulate how quarks would respond, predicting the formation of new particles with astonishing accuracy. These simulations weren't just statistically close, they mirrored the exact trajectories observed in real experiments. When the findings were published in Nature Physics, the response was immediate and polarized. Some hailed it as a new era in scientific discovery. Others questioned whether the AI had truly understood anything or was merely mimicking patterns without grasping the underlying physics. But one thing was undeniable. The AI had done what humans couldn't. It had solved a problem that had resisted every analytical tool developed over 5 decades. Now, the question became, could this approach work beyond physics? If an AI could crack one of the hardest problems in theoretical science, what else could it do? The answer, it turns out, is quite a lot. Researchers in medicine have begun applying similar AI techniques to drug discovery, training models on vast biological data sets to identify compounds that can target diseases like Alzheimer's and cancer more effectively than traditional methods. In climate science, AI is being used to refine global warming projections by analyzing satellite imagery and atmospheric data at unprecedented resolution. Even materials science has seen breakthroughs. AI recently helped design a new class of ultra-efficient solar cells by predicting optimal molecular structures before they were ever synthesized in a lab. These aren't isolated cases. Across disciplines, AI is accelerating discovery in ways once thought impossible. For example, in 2022, an AI-driven project at Stanford University discovered 20 new antibiotics in just 2 months, a process that normally takes pharmaceutical companies years. Similarly, NASA has deployed AI systems to analyze telescope data, identifying exoplanets and cosmic anomalies faster than human astronomers ever could. What makes AI so powerful in these fields is its ability to process vast amounts of data and detect subtle correlations that humans might overlook. Traditional scientific methods rely heavily on hypothesis testing, where researchers formulate a question and then gather data to support or refute it. But AI flips this process on its head. Instead of starting with a hypothesis, it starts with data and lets the patterns emerge naturally. This shift has profound implications. It means that discoveries can come not from a single researcher's insight, but from the collective intelligence of machines trained on centuries of accumulated knowledge. It also raises questions about the role of human intuition in science. If AI can make groundbreaking discoveries without fully explaining how it arrived at them, does that diminish the value of human understanding? Some scientists argue that AI isn't replacing human ingenuity, it's augmenting it. Take the case of AlphaFold, DeepMind's protein folding prediction tool. Before AlphaFold, determining the 3D structure of a protein could take years of lab work. With AI, it now takes hours. Scientists still interpret the results, validate them, and apply them to real-world problems, but the speed at which they can do so has fundamentally changed. Still, not everyone is convinced. Critics point out that AI models are often opaque, what's known as the black box problem. You can see the input and output, but the inner workings remain mysterious. If an AI suggests a new material for battery storage, how do we know it's safe? If it recommends a drug treatment, can we trust it without understanding the reasoning? This debate brings us to one of the most pressing issues in modern science: Interpretability. Can we accept answers from machines we don't fully understand? Or does true progress require transparency? Many experts believe the answer lies in hybrid approaches, combining AI's pattern recognition with human expertise. In fact, some research teams are now developing explainable AI XAI models that provide insights into how decisions are made. These systems aim to maintain the power of machine learning while offering a window into the decision-making process. Others argue that the very nature of scientific discovery is evolving. For centuries, progress depended on human cognition, our ability to ask questions, form theories, and test them. Now we're entering an era where machines can do much of that work autonomously. Whether we call it artificial intelligence or augmented intelligence, the result is the same: faster, deeper, and more precise scientific breakthroughs. Of course, with great power comes great responsibility. As AI becomes more integrated into research, ethical concerns grow. Who controls these systems? Who ensures their findings are unbiased? And perhaps most importantly, who decides how these discoveries are used? That's where the next frontier of AI development begins, not just in improving performance, but in ensuring accountability. Governments, universities, and private institutions are all investing heavily in AI governance frameworks, aiming to balance innovation with oversight. Some countries have already introduced regulations requiring AI-generated scientific findings to undergo peer review before publication. Meanwhile, open-source initiatives are pushing for greater transparency. Projects like Hugging Face's AI models and Google's TensorFlow platform allow researchers worldwide to inspect and build upon existing AI tools. This collaborative approach may be the key to preventing monopolization and ensuring that AI serves the broader scientific community rather than a select few. Looking ahead, the integration of AI into scientific research is only going to deepen. Universities are launching dedicated AI for science programs. Major funding agencies like the National Science Foundation are prioritizing AI-assisted projects. Even Nobel Prize committees are beginning to consider whether AI-generated discoveries should qualify for recognition. As this transformation unfolds, the question isn't just about what AI can do, it's about how we prepare for it. Students today are growing up in a world where AI is part of everyday life. The next generation of scientists will need to be fluent not just in physics or chemistry, but in data science, machine learning, and computational modeling. For professionals already in the field, adaptation is key. Those who embrace AI as a tool rather than a threat will find themselves at the forefront of discovery. Meanwhile, educators must rethink curricula to include AI literacy from an early age. The future of science won't belong to those who resist change, it will belong to those who harness it. And for the rest of us, those watching from the sidelines, this moment offers a chance to engage. Understanding AI doesn't require a PhD. It requires curiosity. It requires asking questions. It requires recognizing that the tools shaping our future are not magic, they're the product of human ingenuity, just like everything else we've built. In the end, this isn't just about machines solving physics problems. It's about humanity taking another step forward in its endless pursuit of knowledge. We've always relied on tools from telescopes to microscopes to extend our reach beyond what our senses allow. AI is simply the latest in that long line of instruments. And like every tool before it, it's up to us how we use it. So the next time you hear about an AI breakthrough, don't dismiss it as just another headline. Think about what it represents. Think about the centuries of accumulated wisdom that led to this moment. Think about the possibilities that lie ahead, because this isn't just the story of an algorithm solving a physics puzzle. It's the story of how we, as a species, continue to push the boundaries of what's possible. Thanks for watching. If you found this breakdown fascinating, give it a like and share it with someone who loves science, or someone who's curious about where AI is taking us. Stay curious, stay informed, and remember, one algorithm at a time, we're building the future.